Another important quantity in the context of circular motion is the angular frequency. So suppose a particle is traveling around in a circle. In one cycle or one revolution, the particle is traveling an angle of 2 pi radians, and suppose it is doing so in a time t, the capital T. This is called the period of revolution. That is the time taken to make one complete cycle. And so the angular frequency omega is defined as 2 pi over t, t being the period. And since the frequency is inversely proportional to the period, we can also write this as 2 pi times f, the frequency. So the angular frequency is related to the actual frequency through 2 pi. The unit of this angular frequency is radian per second. How is the circular motion related to a wave? So over here you see the circular motion of a particle again, but now we place this on a Cartesian coordinate system, x and y, and now we can project the velocity vectors on the x and y axis. And what we obtain are sine and cosine curves for the x and y components, and these are related to theta. So if we plot this, we get relationships that are shown here, sine and cosine curves in terms of theta, and these are basically waves. Another important quantity in circular motion is called the phase. Phase can be thought of an angular measure of the wave and is represented by theta. What it tells us is that what fraction of the wave has traveled, has elapsed relative to the starting position. And over here you see a plot of the wave as a function of theta, its phase. Since waves are a function of time t, theta, the phase, is given by omega times t. Omega is the angular frequency, radians per second, and time is the amount of time elapsed since the beginning. So theta, the phase of the wave, is given by omega times time, the angular frequency times time. Mathematical expressions are frequently used to represent waves, such as sine waves or cosine waves. Over here we show two expressions of waves. Y equals a sine omega t in the first case, and y equals a cosine omega t in the second case. Here a represents the amplitude of the waves. If y is a displacement, amplitude could be in meters, for example. Omega t is equal to theta. Theta is the phase again, and this is given in radians usually. And y is the displacement in meters in this case from equilibrium position. An important case of waves is a simple harmonic motion. So this is the case when the acceleration of an object is proportional to its displacement. And for example, the mass on a spring system undergoes simple harmonic motion if disturbed from its rest position. The spring, if you pull on the mass and let it go, it oscillates back and forth because of simple harmonic motion. Now in this picture you see this system, but there is also a paper, and the paper is moving along one particular direction, and the mass is tracing out a sinusoidal wave as it oscillates vertically up and down. Real waves are in 3 dimensions, so you have to consider their x, y, and z components. Over here you see a circular wave, and notice the arrows here, they point towards the direction of propagation, and the circles represent what are called wavefronts. If we take a cut along any of the arrows, we get a picture such as this, a sinusoidal wave, and the dotted lines here show some of the wavefronts. So what it means is that wavefronts are surfaces of constant phase. Between any two of these dotted lines, the phase is constant. Constant means if the phase changes by a factor of 2 pi, it is basically the same. So the phase is constant. We say the phase is constant. Now this brings us to the definition of wavelength. So this is defined as the distance between two wavefronts. This is measured in meters. Wavelength is in meters and has the symbol lambda. So in the picture in the left, the 2 points that are shown have a constant phase. They are separated by theta equals 2 pi. So the phase is the same basically. Remember, if the phase is a multiple of 2 pi, it is considered to be the same. So this distance between these 2 points having the same phase, this is called lambda, the wavelength. Now let us take a look at this picture on the right. There are 2 points also shown, but the phase is not the same between these 2 points. So this cannot be defined as lambda. What is the amplitude of the wave? This is the maximum displacement of the wave in the vertical direction, in this case, from the equilibrium position. So you can also think of this as the height of the wave. This is measured in meters typically. So the relationship between period and frequency, we have already seen this. So period is the time taken to complete one cycle of oscillation, and it has the symbol of capital T. Its units is second, it's a time. Frequency is the number of complete cycles of oscillations per second. So this is represented as small f, or the symbol nu. It has the units of hertz. Hertz is simply the inverse of a second. Period t is equal to 1 over f. That is, period is the inverse of the frequency. And recall the relationship that we have derived for angular frequency. It was given by omega equals 2 pi over t, which is also equals 2 pi times f. The phase angle refers to how long the wave has traveled after its original position at t equal to 0, for example. This is also sometimes called the phase offset. It is represented by the symbol phi, and since it is an angle, it is also measured in radians. There is a speed associated with a traveling wave, and we can obtain the speed through a relationship between lambda and t. So lambda is the distance traveled in one period t. Then we simply, to obtain the speed, we simply use the relationship distance over time, and this is equal to lambda over t. Lambda is one wavelength. The wave travels a distance lambda in t seconds, and then this gives us, if we use t equals 1 over f, we obtain v equals f lambda. So that the speed of the wave is equal to its frequency times its wavelength. Now let us take a look at the wave equation for a static case. We set t equal to 0 in this case, and we obtain the displacement d from the equilibrium position, x in this case. So the wave equation is of this form: d of x equals d of m times a sinusoidal function, and the argument of the sinusoidal function is 2 pi over lambda times x. Over here, d of x is the displacement, and d of m is the amplitude of the wave. That is the maximum possible displacement at any point. And this shows the graphical form of this equation here. On the y-axis, we have d of x, and the horizontal axis shows x, and we show one wavelength of the wave. So notice that the displacement is 0 at positions x equal to 0, lambda, 2 lambda, 3 lambda, and so on. Now let us propagate this wave, that is, add time to this problem. So in a time t, because the wave is traveling at velocity v, the wave propagates a distance v times t.